All right. I hope everybody's doing well. And so today, what we're going to be discussing is hydration of ketones and aldehydes. So those R's on that can be either hydrogen or carbon. So let's take a look real quick at an aldehyde. So this is formaldehyde, just the most basic aldehyde with two hydrogens on either side. And the addition of water, hydration, forms this diol. It's a geminal diol. Okay. And we have a general trend, just like always. And this is with respect to the reactivity of ketones versus aldehydes. So we have formaldehyde, we have acetaldehyde, and acetone as an example. So as you can see, we're changing one of those hydrogens out for a carbon from formaldehyde to acetaldehyde, and then the other hydrogen to make a ketone, the acetone. As we go from the aldehyde to acetone, we have an increasing stability, and that's because our groups donate electron density, and that's going to be making the carbonyl carbon, indicated with this red dot, it's going to be making it less delta positive. Okay? So what that results in is the trend as we go from acetone to aldehyde, and that trend is going to be an increase in the reactivity. Okay, and by reactivity, what we mean is an increase in the amount of the gem diol or the hydrate. All right, so now what we can do is take a look at the ensuing product or the hydrates that form from these aldehyde, acetaldehyde, and then acetone. And then we'll look at the percentages of each and just to see what we mean by increased reactivity or increased amount of hydrate. So the gem diol for aldehyde on the left, the middle is acetaldehyde, and then on the right we have the one resulting from acetone. So it's pretty straightforward in terms of what the product looks like from a carbonyl group. And we'll go over the mechanism in just a minute, but as you can see, the most basic aldehyde is 99.9% the gem diol. And then with one R group or one carbon, we have 58%, and with two carbons on either side, or the ketone, we have 0.2%. That means it's mostly going to be acetone. Okay, so the way that we can increase the reactivity of a ketone group is by the addition of an electron withdrawing group. This increases the reactivity because it withdraws electron density from the carbonyl group, making it more delta positive. Okay? So this particular substance right here has 3 chlorines on the alpha carbon, and so the carbon adjacent to the carbonyl group, and so that creates a highly delta positive carbonyl carbon, and so we have a substantial amount of the ensuing product or the gem diol. Okay, so since water is a weak nucleophile, these hydrations can undergo 2 different mechanisms, and they're essentially going to be catalyzed by base as well as acid. Okay? And so what we're going to do is go over the mechanisms for those. And first, I want to go over the base catalyzed mechanism, which is, in my opinion, less common. And however, it is still useful. So when we say base, we mean hydroxide, because that's pretty much the portion that we're adding to a carbonyl group when we do hydrations. So let's take a look at what it would be if we had formaldehyde. That hydroxide attacks the carbonyl group, and we end up with this tetrahedral intermediate, or almost the gem diol product. And since it's in the presence of water, we can protonate that alkoxide, resulting in the final desired product. So we'll get that gem diol as well as one molecule of hydroxide forming. So notice these equilibrium arrows. That is because this is an equilibrium reaction, and we can actually go back and forth. Okay, so keep that in mind. And the mechanism for an acid catalyzed reaction is, whenever we're focusing on this particular reaction, we want to make sure that we understand that we are using a strong acid, but we also want to use a strong acid that doesn't really have a nucleophilic byproduct, a nucleophilic conjugate base. So TSOH or H2SO4. Remember, TSOH is para-toluene sulfonic acid. This is something we introduced in first semester organic chemistry. So in the same in this similar type, what we're going to do is protonate this carbonyl oxygen. Now what that does is forms an oxonium ion. That positive charge on that oxygen creates a highly delta positive charge on the carbon, indicated in red, making it more susceptible to nucleophilic attack. We've seen this a million times. And so now that weak nucleophile, water, can attack that delta positive carbon on the carbonyl group, and that kicks those pi electrons up to the oxygen, neutralizing the charge, resulting in almost a gem diol. But we need to do one last step, and that's going to be deprotonation of that other oxonium ion, that trivalent positively charged oxygen. And so now that neutralizes it, it forms the desired gem diol as well as an equivalent of H3O+, which again, the acid is reformed in the end, and that's why the acid is catalytic. That's just the definition of a catalyst. So again, this product is called a hydrate or a gem diol. So you'll see both of the names used interchangeably, and so either one is acceptable. You do need to know both. Okay, that's pretty much all we need to know for hydrates. They're pretty straightforward. The mechanism's good. We got a base catalyzed mechanism as well as an acidic under acidic conditions. And so the next portion of the discussion is on acetals. Now, acetals are much more useful. They're easier to use. Their functionality, as you'll see, is going to be much greater, and so they're going to be a bit more useful than the hydrates. That's why we're going to go have a longer discussion on those. So in the mechanism, I want to point out that base, so B with a lone pair on there, that can equal a generic alcohol or water in solution, and then H plus is going to represent an acid, so H2SO4 or para-toluene sulfonic acid. Or, since those are strong acids, they can protonate the alcohol solvent, and that would lead to the positively charged alcohol that I've drawn there. So acetal formation is under acidic conditions, strictly under acidic conditions as far as we're concerned. And so let's take a look using an acetone this time, a ketone. It's very similar to the hydration mechanism. So what we want to do is we have a strong acid, we want to protonate something, right? And we want to protonate something to help move this reaction along. So we're going to protonate that carbonyl oxygen, forming that oxonium ion, which makes the red dot, that carbonyl carbon, that makes it more susceptible to nucleophilic attack, and it gets attacked by not water this time like in the hydrate, but by the alcohol solvent. So once that attacks, we end up with another oxonium intermediate, which we can use some sort of base to remove that proton and neutralize the substance. So what we end up with here is something that looks very similar. Sorry, I'm going to erase that OH the way it's drawn just for aesthetics. It makes me feel weird when it's drawn kind of silly. So this portion right here, this molecule right here is called a hemiacetal. So it's not quite an acetal, that's our end goal, and it's not a hydrate either because it doesn't have two OHs on it. It's not a gem diol, but it's got an OH on one side and an OR on the other. R being carbon, like a carbon chain of some sort. The simplest one being CH3. Okay, and so whenever you see this highlighted red portion, a single carbon directly bound to an OH as well as an OR group, that is a hemiacetal. Okay. Now this hemiacetal, in the presence of acid and our alcohol that we started with, can proceed further, and what we're going to do is protonate that OH group, giving us this oxonium intermediate. Water is a great leaving group, and so we're going to use the lone pairs on that OR group to create a carbon-oxygen double bond, and that kicks out water. Okay. Now that we've kicked out water, we have another oxonium. So again, this carbonyl carbon is very susceptible to nucleophilic attack. And attack from what? Well, the most abundant thing is the solvent, and so our alcohol, our ROH, is going to attack, leading to another intermediate, the oxonium intermediate, which we can neutralize just by deprotonating with a base, again as noted above, either the alcohol or some sort of a water molecule that comes along. And the final product obtained is an acetal. So the acetal, again, is a carbon that's bound to two oxygens, and on each of those oxygens there's R groups. Okay, so what we're going to look at now is the hydrolysis of acetals. So remember, hydrolysis broke down into breaking up water. Okay, and so this is pretty much just the reverse mechanism of the formation of acetals from ketones or aldehydes. And so we could just look at the mechanism above, but what I want to do is just kind of go over that with you really quickly. And this is going to be in the presence of acidic water. So what I've drawn here is just H3O+. So that could be water with some acid like paratoluene sulfonic acid or sulfuric acid. And what we do is we protonate that OR group, and again creates a good leaving group. That oxygen the lone pairs come down to form a carbonyl or a C double bond O, and since it's a oxonium, that oxygen's got a positive charge and makes the carbon bound to it, the C double bond O, more susceptible to nucleophilic attack. Nucleophilic attack by what? We do have ROH, the alcohol, present, but we have a lot more water, because that's, in this case, that's going to be our solvent. So statistically, the water is going to come in and attack that electrophilic carbon, forming this oxonium intermediate. And we've seen this about 1 million times as well. What we're going to do is transfer that proton to the OR group, the oxygen of the OR group. And so I'll indicate this with another equilibrium arrow as well as proton transfer. So what's that going to look like? Well, it's just going to have another oxonium, but ROH on the left, and then just an OH on the right. So what does that allow us to do now? Well, remember, we wanted to go from an acetal back to a ketone. And so in order to do that, we got to kick off that OR group, or in this case, the ROH. So we have this oxonium intermediate with a hydrogen on the oxygen, which can then just be easily deprotonated by some sort of base, water or the alcohol. And what we get is acetone in the end, or our ketone. We also get 2 equivalents of alcohol, as well as our H3O+. And that would be, if we look above at the last deprotonation step, if we substituted B for water, we remove that hydrogen, forming the H3O plus, indicated in red. Okay, so where did those HOR groups come from? Well, if you look at the original starting material, I'm highlighting the OR groups in red. The starting acetal group had two OR groups, and those OR groups in the final product or in the mixture, the two alcohols, are where those ended up. Okay, so let's put some of this knowledge to practice now. So I'll give you a couple problems, and again, what you want to do is probably pause the video and try the problems on your own and then see what happens. I know we just went over the material, but let's see what we got. So this is a tricky molecule to draw, but what I want you to do is see what this particular molecule will do in the presence of H3O plus. So now think about what we just did. We just went over the formation of hydrates as well as acetals. So what would this classify as? If you look at that carbon indicated in red, we see that it's bound to two different oxygens. And those two different oxygens are bound to carbons. So by definition, that is an acetal. So what does an acetal break down into in the presence of acidic water? Well, it breaks down into either a ketone or aldehyde, and then it also breaks down into two alcohol groups. Okay, so this is going to be extremely useful when we're thinking about that final product. Remember, the carbon indicated with a red dot is the source, or that's where the carbonyl group will be in the end. And so what we want to do is just draw out the molecule and substitute the carbonyl, and then substitute the carbonyl as well as creating those alcohol groups from those adjacent oxygens. And so since that red carbon only has one carbon bound to it as well as two oxygens and a hydrogen, since there's only a hydrogen and a carbon on it, that means that it's going to be an aldehyde. So that's why I've drawn an aldehyde here. And those adjacent oxygens now are going to be alcohols. Okay. So with that, we have the mechanism that we can now go over. So the mechanism is, again, very much the same as above. The only difference would be that it's just a complicated structure. So don't get overwhelmed by the complications of the structure. Just try your best to realize that they're all the same. As long as you can locate where the acetal or hemiacetal is, or the hydrate, then you can do the problem pretty easily after that. So the first step is protonate something, right? We have water, acidic water. So we want to protonate the most basic site on that weird looking acetal, and that's going to be the oxygen. Once we form that oxonium, we actually created a decent leaving group. And so the other oxygen on that acetal can form a carbon-oxygen double bond, forcing the OH to leave. So decent leaving group. Now what we've also created is as indicated in red, that carbon is now very electrophilic, susceptible to nucleophilic attack. And so since we have acidic water, we have water as our nucleophile, and that water can come in and attack. And what that results in is, well, first the CO double bond breaks, giving the lone pair back to oxygen, and then we form another oxonium intermediate, which now we know that we have to neutralize that. So by deprotonating the hydrogen with a base. Remember, that base could be the water or the alcohol. Whatever it is, it's coming along to remove that, to neutralize the oxygen. So one thing I want to point out in a mechanism is, for basic medium, it's okay to form negative charges because we have like hydroxide, for example. But under acidic media, what you usually want to run with is positive charges. Okay, so basic is negative charges, acidic medium is positive charges. Now, it's always best in a mechanism to proceed. The next step, if you do form a charge, is to try and neutralize that charge before you move forward. So that's what we've always been doing, and we kind of know that intuitively, but now I'm explicitly stating it to you guys, okay? So we pretty much did a proton transfer, removal of that hydrogen from one oxygen and put it on another one. And now what we've done is created a good leaving group again. So that CO bond is C double bond O is formed, and that alcohol group can leave. And what we have is essentially the aldehyde that we wanted, but with a hydrogen on the oxygen. But after deprotonation, what we can get is the final product, and as I've circled here, that's exactly what I drew before. So as you get some more practice, you'll be able to just look at the product and then you'll be able to look at the starting material and then just look or immediately go directly to the product. Sorry. So let's try another problem. This one is also pretty fun because it's just an interesting looking structure, right? So again, just like before, what we want to do is look and see what functional group, or essentially like this whole chapter, again, it's easier when we're focusing on one subject, right? We can see that this is an acetal. We have a carbon directly bound to two oxygens, and those oxygens have R groups on it, or carbons. And so under acidic media, what's going to happen? Well, it's going to break down into either an aldehyde or a ketone, as well as alcohols. Now, if we look at that central carbon indicated in red, we can see that it's bound not only to those two oxygens, but also to two carbons. So that's going to tell us that the carbonyl carbon that's formed in the end is going to be a ketone. And I find it easiest to draw it very, very similarly to the way the structure is originally drawn in the starting material, but just break those carbon-oxygen bonds and then form the carbonyl as well as the alcohols. Okay, so both of those were examples of intramolecular acetal formation, which is extremely common. It's also pretty fun because it makes for an enjoyable mechanism, pretty complicated structures, and so it's good stuff. Now what we want to do is focus on acetals from diols and how they can serve as protecting groups. Okay, so first let's talk about what a diol is. So a diol is, if you look at the last portion of that name, it's got the OL, which is usually indicative of an alcohol. And so di meaning two, ol meaning alcohol. So what we get is two alcohols, but within the same molecule. So this is ethylene glycol drawn on the left, and then let's see what it does to form an acetal. So let's use acetone as a basic ketone. So again, we still need our acidic medium, and I'm going to draw the diol in red just to allow you to see what bonds are formed from that diol. So we get this cool looking structure right here where it's a ring structure. It's kind of weird looking, but again, it's exactly what we've seen before for acetals. So the first step, protonate that carbonyl oxygen, resulting in that oxonium, and again, that makes the carbonyl carbon more susceptible to nucleophilic attack. Okay, a nucleophilic attack from what? Well, the alcohol that's in solution, and that being the diol. So one of those oxygens can come in and attack, neutralizing that positively charged oxygen, resulting in a neutral OH. And now we've got the diol hanging on to that carbon, also bearing that new positive charge. And so essentially, this mechanism is going to be exactly the same as we've seen in the past, but just it looks a little bit different because that alcohol is no longer floating around as the solvent. It's kind of just stuck in close proximity to the actual ketone molecule, or at least the starting ketone molecule. So what we're going to do is a proton transfer. We're going to remove that hydrogen from the diol oxygen and put it on the OH, the other OH, to create a good leaving group, water. So we create a carbon-oxygen double bond to kick that water group out, and this oxonium ion again creates a carbon that's susceptible to nucleophilic attack. This is a very quick process because it isn't an intramolecular nucleophilic attack, and so this is an extremely favorable process. And so after the oxygen attacks, we neutralize the oxygen. We also have, I'm just going to move on and remove that proton, resulting in that final acetal product. Sorry. So let's take a look at a couple problems and put this to practice. So what I want to do is I want to draw a really complicated structure and with lots of oxygens, and what you should be able to do is just to point out where an acetal is, or where a hemiacetal is, or a hydrate, and understand what can happen in the presence of acidic water, essentially. So let's take a look at this guy, for example. There's way too many oxygens, right? There's all kinds. However, there are only 2 acetal groups. Okay, so pause it, think about it for a second, trying to locate those, and then think about also what's going to happen in the presence of the H3O+. So I've highlighted one acetal in red here. Okay, and now what we want to do is point out that there's a hydrogen on that, right? So what is that going to help us understand? It's going to help us understand what the final product is going to look like after hydrolysis occurs. So now that we know that there's a hydrogen on there, we know that the other side is a carbon, so it should form an aldehyde, as well as 2 alcohols from those highlighted oxygens in red. The other side, we've got another acetal, and that carbon right there has 2 carbons on it. So we know we're going to form a ketone. Now, if we look at the oxygens on the left side, those are just traditional ethers. So again, this is actually important to notice. Those ethers are not the same as an acetal. Even though it's a carbon, oxygen, carbon single bond, acetals react very differently. And we've seen this in the mechanism. The reason is because of resonance stabilization. And so as we cleave those bonds, I've created the OH on the left side attached to that benzene ring, and now we've created the OH and the aldehyde on that other portion. Now we've got 2 OHs on the other side, and then an acetone compound forming as well. And so this, again, with practice, will be very easy. You shouldn't even have to think about it eventually to know what's going to happen. The key thing, in my opinion, is to note that find out where the carbon that has 2 single bonded oxygens to it, and then see what else that carbon has. Does it have 2 carbons on either side, or does it have a carbon and a hydrogen? If it's a carbon and a hydrogen, that's going to be an aldehyde. If it's 2 carbons, that's going to be a ketone. Those oxygens are going to break. You're going to break that carbon-oxygen single bond and form alcohols on the oxygen. So if we looked at this new guy, we can quickly determine that we have an acetal only on the right side. So that acetal carbon has 2 carbons bound to it, so it's a ketone. Now those other oxygens have methyls on there, and so what we end up getting is 2 methanol groups. It's as easy as that. So again, I want to point out that acetals are not ethers, they are acetals. So the reason why is because as we saw in the presence of H3O+, the ethers on these last two molecules did not react. The acetal reacted first. It's much more reactive. So under different conditions, yeah, maybe the ether can react. However, under mildly acidic conditions, the acetals are what's going to break down. So it's just really important that we understand this, because this is going to be useful for other mechanisms that we'll see later. Okay. All right, so now what I want to do is go over a naturally occurring acetal. So anything natural and having to do with chemistry is super intriguing to me, especially when it comes to natural products that cause cancer. Especially when it comes to natural products that cause cancer that they used to put in tasty beverages such as root beer. What you talking about, Willis? Well, this molecule right here is safrole, and it comes from the plant sassafras. That's also happens to be one of my favorite words, because sassafras is fun to say. But turns out, bummer if you liked root beer back in the day, because it was carcinogenic. So, oh no, mama, no, why? Why is it carcinogenic? Why is my favorite beverage cancer causing? Well, let's take a look at what it breaks down to in the presence of H3O+. Well, let's look for our acetal. So what we've got is a carbon bound to 2 oxygens. Remember, what is that carbon bound to also? 2 hydrogens, right? Okay, do. So now we quickly break that down into an alcohol. And then, but what does that acetal carbon turn into? Well, that acetal carbon, again, is going to be a carbonyl with 2 hydrogens on it, which is the most basic aldehyde, known as, you guessed it, formaldehyde. So, not sure if you guys know, but formaldehyde is carcinogenic. So it's actually used to preserve like animal species, or like in the bio department, cadavers. And so it could also be in the form of formalin, which is just water and formaldehyde. So what the heck? Formaldehyde in my root beer? Pissed. So that's why it's no longer used in root beer. So if you ever go back in time, bring that one thing. You at least got that. Tell people, don't put sassafras in your root beer, because it's gonna release formaldehyde, which is carcinogenic. All right, so we have another practice problem. We have this cyclic ketone, cyclohexanone, with ethylene glycol, aka our diol, and then boom, what does it form? It forms this fancy looking acetal. So we should know how to do this. Just jump straight to the product again. Okay. All right. So let's get a structure that's actually a little more complicated, or maybe not complicated, but just a little bit more to think about. So we have a ketone carbonyl, as well as another carbonyl coming from an ester functional group. So if we threw our diol in acidic medium, what would we form? The question would be, are we forming an acetal on the ketone or the ester? Well, it turns out that the acetal forms on the ketone selectively. So what is it about this ester group that makes it less reactive towards the diol? So why the ketone, in other words, right? So what's helpful is if we look at the resonance structures of both of these particular groups. So I'll write a basic ketone, acetone, and if we draw a resonance structure, we can see, again, not my favorite resonance structure ever, but helping us understand that we have a delta positive on the we have a positive charge on the carbon and a negative charge on the oxygen for one of them. But for the ester, we have, rather than 2 resonance structures for the ketone, we have 3 resonance structures for the ester, and a positive charge on the carbon and only one of them. That means that for the ketone, we have 50% of the resonance structures have a carbocation, indicated as C+, but for the ester, only 33%, or 1/3 of the resonance structures contain a carbocation. So that means that the ester is less reactive, at least with respect to this particular mechanism. Okay, so this is actually an extremely useful tool, because now what we can do is use it as a protecting group. Okay, well, the question is, why is the acetal a protecting group? Well, first I want to let you know I'm going to abbreviate protecting group in any of the videos as PG. We already know this, but just letting you know again. So let's draw an acetal. So the reason why that's a protecting group is because it's resistant to oxidation, as well as reduction, reactions with base, and reactions with nucleophiles. So this allows us to do a variety of reactions to other things in a molecule that don't have that acetal on them. So in this case, if we wanted to reduce with lithium aluminum hydride, this ketone and ester containing molecule, what we would do is reduce the ketone first, making the alcohol there. But what if we didn't want to do that? Well, what we can do is add the diol in acidic medium, making the acetal, then reduce with lithium aluminum hydride, because the acetal is resistant to reduction, as indicated above. And so now what we end up with is, not the ester, the alcohol. And our acetal is untouched, which we can then hydrolyze with acidic water, and that gives us our ketone back as well as the alcohol. That's why acetals are so useful. That's why they're good protecting groups. They're so resistant to other chemical reactions. All right, so let's take a look at cyclic hemiacetals. So remember, the hemiacetal was a carbon that had an OH as well as an OR group on it. I'll draw that mechanism for you real quick. Let's use acetaldehyde as an example. In their acidic medium, we protonate that oxygen, form the oxonium, makes a carbon that's more susceptible to nucleophilic attack by an alcohol. That attacks, yada yada, we get minus a proton in the end, and what we end up with is our hemiacetal product. A carbon bound to two things, it's like a hydrogen and a carbon, a CH3 in this case, as well as an OH and an OR group. So this hemiacetal, let's imagine that our group was actually not just dangling off, but cyclic. So that dotted red line is now that imaginary ring. So what it might look like is something like this, like a cyclohexane, but with the oxygen in the ring and an OH coming off. So that carbon in red is the same as that other example hemiacetal. Now the R group is just the ring portion attached back to that acetal carbon. So typically these are going to be 5 or 6 membered rings because these are most stable. So we already know from last semester that 6 membered rings are the most stable. 5 membered rings aren't actually terribly unstable, and so these are the two most common ones that we'll see. A little hint at that would be like sugars especially. So let's draw our hemiacetal, our cyclic hemiacetals. We've got the highlighted portions here just to show you where the hemiacetal carbon is, and just to also to point out how stable these are. 94% of the cyclic hemiacetal for the 6-membered ring and 89% of the hemiacetal for the 5-membered ring will form if you have, well, how? If you have something called a hydroxyaldehyde. And so that would mean that we would have to have an aldehyde as well as an OH group in the same molecule. So it's going to be an intramolecular reaction. So what is that going to look like? So this is an example of a hydroxyaldehyde, and if we count the carbons, we've got 1, 2, 3, 4, 5 carbons, and then that oxygen is the sixth member of that ring. Okay, so let's protonate that carbonyl oxygen, as that is the first step in the formation of a hemiacetal. That gives us an oxonium ion, so that carbon is more susceptible to nucleophilic attack. So remember, intramolecular reactions are always faster than intermolecular because they're already in close proximity. So that oxygen on the other end of this hydroxyaldehyde can attack, and that neutralizes the oxygen, the carbonyl oxygen, and forms the six-membered ring with the OH on there. After deprotonation of that new oxonium ion, we get the desired product. So again, this hydroxyaldehyde gives us 94% of the cyclic hemiacetal in the presence of slightly acidic medium. So pretty cool. So now what I want to do is use this hemiacetal product to get into the next topic of our discussion. So imagine we had this hemiacetal in the presence of acid and alcohol. So methanol, for example. So what we're going to do is form an acetal, or a cyclic acetal, from a cyclic hemiacetal. Okay? So again, we already know this mechanism. This is the same mechanism that I gave you above, or before, but we'll go over it again. So protonation of that OH group by that acid forms a good leaving group, water. That water is going to get forced out by the lone pair on that oxygen in the ring, forming this ring structure with an oxonium in it. That carbon is very susceptible to nucleophilic attack. By what? The alcohol, because that's probably the solvent, and that's going to be in high abundance. We form a new oxonium. Deprotonation with the base gives us now an acetal, a cyclic acetal from the original cyclic hemiacetal. So this is fun stuff because this is related to sugars again, but the cyclic hemiacetal, the cyclic acetal again can be highlighted. We have a carbon bound to two separate oxygens, singly bound, and then we also have on those oxygens carbon groups. So CH3 on one, and then the rest of that ring on the other. So this is again going to be what screams out to us, cyclic acetal. So maybe one of the funnest parts of acetal formations is the topic of sugars. So carbohydrates, if you want to call it that, but sugars because it's tasty. So what you've probably seen glucose represented as is this ring structure right here, right? This is beta D glucose. You may have also seen it drawn like this, where you have a flat ring structure with OHs sticking up and down. And this is called a Haworth projection. So if you haven't seen it before, that's okay. I'm just trying to introduce the many different looks of sugars and how they can be represented. Another way that you've seen it, which I know I've shown you in class, is linear glucose. So this would be represented as a Fischer projection. So the above two are obviously cyclic glucose, but the Fischer projection would be in the form of, we have an aldehyde and we have an OH group going right, left, right, right. That's how I remember glucose, or D-glucose at least. And then these other portions are hydrogens, right? So again, this is going to be D-glucose. So why is it called D-glucose? Where did that come from? Well, D as opposed to L would be left and right, correct? So the reason why it's a D-glucose is because the OH is on the right side. That's all it is. But it's on the right side in the Fischer projection. So that's why it's important to let you guys know or remind you what a Fisher projection looks like. It's also important to remind you what this Fisher projection allows or requires us to assume or understand. So this very, very block, like straight lined linear drawing of the glucose in the form of that Fisher projection, it requires us to realize that each of those horizontal bonds is actually a wedge. So there's a wedge OHs and wedge hydrogens, and this allows us to assume the stereochemistry of this particular sugar. So this is important because this is D-glucose the way it's drawn. If you swap one of those OHs from the right to the left, that's a different enantiomer, because those are all the wedges drawn there in that Fisher projection are going to be stereogenic centers. So if we swap one of those to one of those OHs, it's a totally different molecule, a different sugar. Okay, so let's take the black Fisher projection, and rotate that 90 degrees on its side. What we have is a sugar. It's still a Fisher projection. It's just another way of looking at it. And I want you to look at the OHs. We have going from the aldehyde across, we have a OH going down, up, down, down. Okay, we're going to ignore the terminal OH because that's not a chiral center. So I've also highlighted starting from the carbonyl carbon in red. I highlighted 1, 2, 3, 4, 5 carbons, and then that 5th carbon I've highlighted the OH. This is 6 members, and these 6 members are what's involved in forming that cyclic glucose. So let's rotate this, basically bend this Fisher projection around itself to start forming that cyclic sugar. And what we have is the structure drawn on the right. Sorry, it's not beautiful, but what we can see is that we have what looks like almost a chair conformation. This is intentional. So what we want to kind of look at is the OHs in the Fisher projection that we had them down, up, down, down. If we look at what looks like a chair conformation almost, we have our OH going down because it's not axial. The next OH is going up because, again, it's not axial, and then down, down for the last two. And this is starting from the carbonyl carbon, working our way around. So again, it goes down, up, down, down. And what we need to do now is focus on the OH in the back that's bound to the CH2OH. So I've drawn above what looks like a generic tetrahedral carbon bound to an R group, an OH, CH2OH, as well as a hydrogen. So I've tried to make it look like the almost ring structure drawn below it. And now imagine if we rotated those 3 substituents, the OH, CH2OH, and the hydrogen, and we rotated around the axis of that R group. What we would do is have them swap. So now we have the hydrogen on the bottom, and then the OH is now the wedge, and the CH2OH is the dash. So this is actually the conformation that's going to allow us to form cyclic glucose. So again, what we have is what looks exactly like the ring structure of glucose, but if we look more closely, we can see that we have an aldehyde in the presence of an alcohol. So this is like that hydroxyaldehyde, that example that we just drew above. So I've also highlighted 1, 2, 3, 4, 5, 6 portions of this almost ring, just to show you that we're forming a 6-membered ring from these specific atoms. Now, how's this going to happen? Well, in the presence of acidic medium, we have protonation of that carbonyl oxygen forming an oxonium ion. And sorry, it's just going to take a minute because we got to draw out all the OHs. Again, pointing out down, up, down, down. Focus on that when you're drawing this on your own, just to point out how this Fischer projection affects the stereochemistry of the resulting cyclic sugar. So now we've got that oxonium ion, makes it more susceptible to nucleophilic attack by that oxygen, and this forces the pi electrons back on that oxygen, neutralizing it, creating a new oxonium ion, which we can then deprotonate with the presence of base, probably water, and now what we have is cyclic glucose. We fancy, aren't we? So there's actually two forms of this cyclic glucose. We can get where the carbonyl carbon, or the carbonyl CO was, we can have that particular OH be in the axial position pointed down or in the equatorial position pointed up. Well, axial is alpha D glucose. Axial is also starts with an A, alpha is A, and equatorial is going to be the beta D glucose. Well, which one do you think is more stable? The OH in the equatorial position, right? That's going to be the most stable. And so we do have a higher percentage of beta D glucose. However, it is going to form both. And this is going to depend on how that OH attacks. So I circled it above. When that OH attacks the carbonyl carbon, it can attack from the top or the bottom, and this is going to force the OH down or up. Some pretty cool stuff, right? What we also want to point out is that this cyclic glucose is a hemiacetal. We have a carbon bound to two oxygens. One of them is an OH, and one of them is an OR, or O carbon group. So there you go. That's why the hemiacetals were important intermediates to remember. So sugar dimers or polymers are actually cyclic acetals as well. So they could contain, or they definitely do contain, acetals as well as hemiacetals on the terminal position. So let's take a look at this sugar. So if we look at the location of these OHs, we have on the far left, that one is now pointed up in the axial position, as opposed to glucose above, which was in the equatorial position, pointed down. That makes this beta D galactose. And it's beta because the OH on the right is in the equatorial position. So next to that, I have beta D glucose. So these two things can actually react with one another. In the presence of acid, what we can do first is protonate that oxygen on the right, forming essentially water, which is a good leaving group. And once we form that OC double bond, we can force that water to leave. And what we formed in this particular step is an oxonium ion with a carbon that's very susceptible to nucleophilic attack. By what nucleophile? Well, if we look at the beta D glucose, we have a bunch of OHs. Now remember, OHs, this is pretty much a bunch of alcohols, right? So when we used alcohols throughout this discussion to make acetals as well as hemiacetals. So in this case, yeah, the OH on glucose is going to be our nucleophile, specifically the OH on the far left, which is the fourth position from the oxygen. So once that attacks, it neutralizes the oxygen on galactose, and after removal of the proton from that OH, we end up with a dimer. Okay, and so this dimer is going to be drawn a little bit weird. It's not weird, it's just different to us. So we're going to have to force this sugar molecule down, and the reason why is because we want to maintain the geometry of all of these things. So that equatorial position, the OH, it was pointed down. So if we rotate this dimer molecule, we can see that the structure of this glucose monomer is the same as it was above, before or during the nucleophilic attack. And if we saw the structure of the galactose before, we could see that it was the same as well, with the oxygen in the equatorial position. Turns out this dimer is lactose. So lactose consists of glucose and galactose, and that's how it's formed. You form an acetal between the two sugars, and then if you look on the far right of lactose, you can also see that there is a hemiacetal with that OH on the far right. So let's try another one. So this particular dimer is maltose. So maltose is formed in the same way as above when we formed the lactose, but maltose is formed from two, try and guess. What do those monomers look like? They look like two glucose molecules to me. So we have the maltose. What we want to try and do is label the acetals as well as the hemiacetals positions. What we want to do after that is see what happens when we introduce acidic water. Also, not in the same reaction, separate reaction, introduce acidic methanol, and then a third reaction, sodium hydride and methyl iodide. So the first portion, identifying the acetals, I've highlighted the acetal portion in red because we have that carbon singly bound to two oxygens, and then those oxygens are bound to carbons. By definition, that's an acetal. And on the far right, we have a carbon singly bound to two oxygens, two separate oxygens, and then one of those oxygens has a hydrogen and the other has carbon. So that is by definition a hemiacetal. So next, what we want to do is see what happens when we add acidic water. Well, this is going to be hydrolysis of the acetal, and so what we're going to form is two glucose molecules, as drawn here. Okay, this is just cleavage of that acetal portion. Okay, so the next step is, or the next reaction is methanol in the presence of HCl. This again is going to be hydrolysis as well as acetalization or acetalization. So imagine we cleaved those bonds, right, to make the two glucose molecules, but now we have a hemiacetal on the far right of that molecule, that glucose molecule. And we know that hemiacetals in the presence of alcohols and acidic medium results in the formation of an acetal. So that's where we only get the OCH3 substituted on that far right oxygen because that is part of the hemiacetal. All the other ones are just alcohols. They don't react the same. But if we wanted to make those OHs on the rest of the glucose molecule OCH3, what we can do is the third reaction. If we add sodium hydride, that's a base. We're going to remove all the hydrogens on the OHs, and that makes strong nucleophiles, alkoxides. And so the RO minus can attack CH3I or methyl iodide, and that's just a substitution reaction, SN2. And so what ends up happening is we get OCH3s on every single one of those OHs. So there's a variety of reactions we can do with sugars, and it's really important that we understand the selectivity of these different functional groups on here and the different types of reactions we can do with them. So again, acetals and hemiacetals are not ethers. They react differently. They're also not even going to be the same as a typical alcohol. Okay. So the last little bit that I want to point out is the homework. So on the left side, I have the homework for this topic. So 1843 BF and then all the way down. On the right side, since we had in-person lectures for the beginning portion of this chapter, I want to kind of introduce or assign the homework for that. And so those homework problems are going to be related to like Grignards or cyanohydrins. They might have a little bit of other stuff in there as well that's related to amines, enamines, and acetals, and etc. So let me know if you have any other questions. I hope this video helps you, and stay healthy, wash your hands. I almost forgot to leave you with a lovely joke. So, what did the thermometer say to the graduated cylinder? Psh, at least I have a degree. Ah, okay. It's cool. It's cool. I mean, you say you're a 10, but I mean, maybe on the pH scale, because you basic. Bye, Felicia.